So section 10.3, vector valued functions. We actually have something called two standard unit vectors, and those are vectors I and j. So vector I is 1, 0, and vector j is 0, 1. So they're both unit vectors, meaning length 1. What this is going to allow us to do is write any vector, AB, in component form. Instead of having AB, I'll have vector A0 and add that to vector 0b. Then I'm going to factor out an A, and I'm going to factor out a B. So what this allows me to do is write my vector as AI plus BJ. I can say my vector AB is A times vector I plus B times vector J. This part right here with the I is called the horizontal component, and the other part would be called the vertical component. Let's see about expressing vector u plus v as a linear combination of I and j. Vector u is 5, negative 2. Vector v is 3, 4. So if I want to write vector u plus v, I can think of this as 5i minus 2j and add that to 3i plus 4j. So I have 8 times vector I plus 2 times vector j for my answer. So now we're going to go into what are called vector valued functions. You're going to have x as some function of t, y as some function of g, where t is going to be representative of our time. So if we talk about the position as xy, we can say that the position as a vector valued function will be f of t and g of t, and then we can translate to what's called a position vector, and we use vector r of t, or we can write f of t times vector I plus g of t times vector j. So this is what's called a vector valued function. Now a couple things about these that you should be aware of. The velocity vector, v of t, is what you get when you take the derivative with respect to time of our position vector. We can also calculate the magnitude of vector v, and the magnitude of velocity is the speed. We can say that the acceleration vector, a, is the derivative with respect to time of your velocity vector, which is also the second derivative of your position function with respect to time. And then one other thing to go with this is that we say that the velocity divided by its magnitude, which is a unit vector, is what is referred to as the direction of motion. Let's do a couple calculations here. Let's say vector r of t is cosine 2t times vector I plus 2 sine times vector j. I want us to find the velocity vector and the acceleration vector. So of course for the velocity vector, you just need to take the derivative with respect to time of your position function. So we can derive cosine 2t, which is going to be negative 2 sine 2t times vector I, and then take the derivative of 2 sine t, which is 2 cosine t times vector j. Now I want to find our acceleration vector, so that means I need to take the derivative of our velocity vector. So take the derivative one more time. I get negative 4 cosine 2t times vector I plus a negative 2 sine t times vector j. Now how about let's do one more thing with this. How about let's find the particle's speed and its direction of motion at time t equals to 0. Speed is the absolute value of the velocity vector. So I need to take the absolute value of our vector, and I'm going to write this time in component form, negative 2 sine 2t and 2 cosine t, at time t equals to 0. Sine of 0 is 0, cosine of 0 is 1, so it's 0, 2, and the magnitude of that vector is 2. So now we need to find its direction of motion. Well, direction of motion is the unit vector. So we take our velocity vector and divide it by its magnitude. This one's pretty easy. 0, 2 divided by 2. So we have 0, 1. Let's find the equation of the tangent line and normal line to vector r of t equals 2 cosine t minus 3 times vector I plus 3 sine t plus I times vector j at time t equals to pi over 4. Let's first just work on the tangent line equation. The tangent line equation is really the slope, and we need to know the y-intercept. We need to find the slope, or dy dx, at time pi over 4. So if we're trying to find slope here, that means we again need dy dt over dx dt, just like when we did them with the parametrics. So what's dy dt? 3 cosine t. And dx dt is going to be negative 2 sine t. So I can simplify that to be negative 3 halves cotangent t. Now we want to evaluate this when t equals to pi over 4. Cotangent pi over 4 is 1, so our slope is negative 3 halves. Now the other thing we have to do in order to write an equation of a tangent line is to have a point that it goes through. So I need to find the point, and this is going to occur when our vector r is at time t equals to pi over 4. So let's plug that in. 2 cosine pi over 4 minus 3 times vector I, 3 sine pi over 4 times vector j. So cosine pi over 4 is radical 2 over 2. So I get radical 2 minus 3 times vector I. And then I have 3 radical 2 over 2. Oops, I forgot something over here. Plus 1 times vector j. So plus 1 times vector j. So this is our point. We have our x value, and then we have our y value, because you can think of this as a vector in component form as well. So the equation of our tangent line I can write out using point-slope form, and that's going to be y minus y1 equals to m times x minus x1. And I'm going to go ahead and leave the equation like this and not write it in slope-intercept form. There's nothing that says I had to. And then we need the equation of the normal line. Do we really need to do a whole lot more work for this? Not really, because a normal line is simply perpendicular to the tangent line. So we're going to have the same equation basically. It's going to go through that same point, with the exception of what? Our slope is going to have to change, and our slope is going to be the negative reciprocal of what we have, so we're going to use 2/3. And there are two equations, one of a normal line, one of a tangent line.